Good afternoon, everyone. I am Pampa from Physics Department, IIT Bombay. First, I would like to thank the organizers for giving me this opportunity to present our work here. Today, I am going to talk about run and tumble like motion of Marangoni swimmer. It is an experimental based project. We proposed a simple toy model to validate this system. Also, I would like to thank my supervisor, Professor Puneet Paramananda, and Professor Amitabh Nandi, and my collaborators, Abhishek and Ars, and all of my NLD lab members for their support and suggestions. So, we all know about the bacterial, different type of bacterial motion, gliding, twitching, and run and tumble. So, it is a trajectory of E. coli bacteria where E. coli is moving towards the favorable condition. It is called as run, and changing, if it is not favorable for it, it changes the direction, it is called tumble. It is the corresponding speed profile of it. There is a dip which shows the tumble. So, it is not only limited to the living system, it is also people have observed this kind of behavior with the non-living system. This is a recent work where they have used phenanthrelin disc within a Fe2 plus solution, and this is also another non-living system. This is a camphor graph which shows this linear motion and the circular motion. These two systems work with the Marangoni flow. So, in our lab, we designed a Marangoni swimmer which is able to show 3 different states: run, tumble, and the rest states. We are calling it as a Marangoni swimmer. It is camphor infused. Okay. Before going to, why it is not working? So, before going into the detail of our project, first you should know what's the Marangoni flow. This video shows the if petri dish is filled with water. In the water, top of the water level, there is a paper flex, and they used 1 drop of surfactant which reduced the local surface tension, and there is a flow from the low to high surface tension. This flow is known as the Marangoni flow. We use this concept and performed all of the experiments. So, we first prepared the camphor solution using ethanol and the camphor, and we inspired from this paper how to make the camphor pen. So, we made different concentration pen, suppose 1 and 1.5 molarity, and then we took A4 size paper and cut this paper as a trapezoidal shape, and this then we have drawn a camphor pattern on it. This is an asymmetrical camphor pattern, and then we put this swimmer, we are calling it a swimmer, so on the flower shaped container which is filled with the water, and started to observe the motion. So, this motion it is releasing the camphor on the water and producing the torque. So, the resultant due to releasing of the camphor, it is producing the gradient, surface tension gradient, and the resultant force. If the force comes from the top of the center of mass, it will show the counterclockwise. If it comes from the below of the center of mass, it will show the clockwise, and if it is from the bottom to top, it will show the run. So, we have observed that this there is a intrinsic chirality of this system. We have drawn the different pattern which is mirror shaped of the previous one, where the counterclockwise rotation was more prominent. We continued with our system with the first pattern where the clockwise rotation is more prominent. It is a stochastic process. There is no predictability when which states will occur. Therefore, we characterize our system and categorized into 3 states. There is a translational speed and the rotational speed. If and there we manually put this threshold value for the translational and the angular both. If the angular speed is less than the threshold value, then we consider it as a run state, pure run state. If a translational speed less than the threshold value, we consider it as a tumble state. If both of them are less than the threshold value, we calling it as a rest state. It is one of the experimental movie where the green vector shows the orientation of the swimmer and the red one is the velocity vector. It is now it will show the run and then it will show the tumble. When it is tumbling, there is a 90-degree 90-degree angle difference between two vectors, velocity and the orientation vector. So, yeah, so these are the snapshot of the three states. We have seen that in our system, tumble and the rest states are more frequent compared to the run state, and the consecutive tumble states and the run state and the rest states there is no correlation. This is a return map plot. So we can predict from this plot that the system is stochastic. Our experimental system is stochastic, and this is a residential time statistics plot where the rest and the tumble time is higher than the run state. We defined this as a sigma. Sigma is 0, 1, 2. Then we proposed a simple model to understand the system. We consider it as a chiral active Brownian particle. So there is a switching rate from rest to tumble, tumble to run, and run to rest. So we take the switching rate is considered as the probability between two states and the inverse of the multiplication with the inverse of the residential time, what we have calculated from here. And then we put this transition rate into the using the Gillespie algorithm, and we produce the new state from the simulation. And these states we used in the overdamped Langevin equation, and depending on the sigma value, it will show different state motion, and these are the corresponding trajectory. Here we only tune the thermal noise and the rotational diffusion coefficient. We have observed that for smaller value of the rotational and the thermal noise, it matches with our experimental system. Here it is a mean square displacement plot where we have seen the run time, there is a ballistic motion which within the 1.1 second, and the dip has been observed at the tumble time scale, and this is the exponent plot. To understand the exponent clearly, we have taken the derivative of the MSD, and the diffusion coefficient should be less than the tumble time scale, inverse of the tumble time scale. Okay, so in summary, this is our experimental trajectory where we have observed three-state system, and it is stochastic, and then we proposed a model, a simple toy model, and here is the mean square displacement plot which shows the different time scale behavior, and this motion is clear before if the simulation time scale for the rotational diffusion should be less than the tumble time scale. So that's it. Thank you so much.
There's a question over there.
I was unclear to me what made this the particle. What determined the orientation of the particle, the natural? You have that arrow, so
it is the orientation like with respect to the center of mass, like.
But because of the shape?
Yeah, because of the shape. So in this movie, it is here, I think.
Okay, I see.
Can you explain the MSD plot once again? Like,
Yeah.
and what are the features of it?
So yeah, I skipped. So it is initially, there is a ballistic motion for a short time scale. There is a slow crossover. I think this slow crossover is coming due to the tumble on the rest state. So first we were confused with this slow crossover, and then we plotted this exponent, and here in this exponent you can see there is a dip. So this dip can be controlled with this parameter lambda. So it is, if you reduce the value of lambda, the tumbling radius will be increased, and the deep of this exponent will change also. It will be more deeper. It will go. So that's the point. I think am I
Is there-
able to address?
Yeah, and is there a reason like why the exponent like goes a bit wild when you look at
It is
large time?
this is
Yeah.
it is coming at a fluctuation only.
Okay. Okay. Thank you.
The,
Yeah.
the rest motion I understand would be decoupled from like both the run or tumble motion, but in no cases are you seeing running and tumbling together. Like you're defining all three motions as like all three states as entirely separate, and in some sense like if one is happening, another is not happening. It's succession of run, then tumble, then rest, and then run and tumble. You don't see. It's not possible to see like say run and tumble together, where it's rapidly rotating but also moving
Yeah,
like translationally at one
yeah,
point. Is anything preventing that is what I'm asking.
Can you repeat? I don't.
Is there any reason why we should not expect these two events to happen together, for example, these two states to coexist?
Because of this shape, of the swimmer. Because actually, when I have already mentioned that it is releasing camphor, and it is sometimes the gradient forms in such a way it is producing this straight run motion, and it is not in our control, and most of the time it shows the chiral motion, this rotational, but I think the shape is responsible for this. There is no any other reason. Yeah. Sir.
So in the run state, is it possible for you to just paint the camphor differently and make it run with the fat end forward?
I don't get.
Can the particle run with the fat end forward? Now it's running with the thin end forward.
Yeah.
Can you?
Can you?
Can you?
Okay. After some time, it can go like okay. So your point is
Can you change the paint?
change
the pattern of the camphor and make it go fat and forward.
Yeah, that depends. Proportionality. It depends on the proportionality of the camphor. If the shape is same, if the gradient, if I draw the pattern in the reverse way, I don't think it can show different motion. I don't know what kind of motion it will show. I can show you one thing. I think that makes it clear. Yeah. So this is a very simple explanation. If I take the rectangular shape and draw the pattern, it will mostly show the force will be balanced from this side, and it will show the straight run. If I start to increase, there is a chance to rotation. So that two things matter: the shape of the paper and the pattern. So I don't know what will happen there.